І запрошуємо вже сцену нашого друга з Польщі, це Мартіна Кучеру. Марцин сюди. У нього буде дуже цікава доповідь. Це GPON, XGPON ONU, основний огляд з точки зору постачальника обладнання. У нас вже був цікавий доклад в тому році. А, якщо можна, пульт, да, будь ласка, да. So, let's start. Марцин Кучера ще раз, да. Це ідейний наставник LeoLabs і дуже цікава доповідь про нові рішення GPON та XGPON.
Can you hear me? Thank you. Sorry, I will use English because my Ukrainian is not yet perfect. Yeah. Okay, here it is. The company, first of all, the title, GPON XGSPON ONU under the hood, because we make these devices. I mean, we don't have a factory physical, but we do the software. We do work with designers to design the hardware. I can tell you a bit more about what is inside and why sometimes you can expect something more from this hardware, sometimes you cannot expect anything more. Our company, LeoLabs.pl, is one leg because we have two companies. One is ISP, so telecom, and the other is vendor because it is not good to sell equipment as ISP, so it's better to have a separate company to sell it as a vendor. So that's why we have it. And just having this other company, which is Leon, is very good because we have a very large live test lab where we can test our equipment, we can do interoperability tests, we can do the user experience test, and that's very okay to have live telecom network as a vendor for testing purposes. So Leon is a regional telecom with own FTTH infrastructure and has a lot of subscribers and does the own R&D. So yeah, that's an example of cables, not all of the cables, and this is a bit old map. We have more now. Over 1,000 kilometers of own main cables, not counting all the cables which are to the subscribers. But in fact, when you look at the entire Poland, it's okay. The map is not shown too well, but it's very little. It's only there. Now, about the devices that we do. First of all, some kind of dictionary a bit about some abbreviations. SoC, System on Chip. If you buy a computer, you have a CPU, processor, like Intel Xeon or any other, or AMD or something like that. Here, the processor has the switch, has the GPIO, has the CPU cores. Some of them, they have MIPS cores, so it's not Intel like x86, it's different MIPS. Some newer one have ARM, like A55 platform. They can have 1, 2, or 4 cores, usually, what I have noticed. Switch engine. There is a little switch chip inside, which is responsible for Ethernet ports, for switching of layer 2 traffic. It's built in. Also, if this device is able, this chipset is designed also to be a router functionality, it will have additional routing engine. So it's a NAT L3 engine, I call it. Most recent are based on RISC-V processors. So there are like 2 or 3 cores extra of RISC-V, which are designed for the purpose of making layer 3 and the NAT processing. Ethernet ports, physical Ethernet ports, like conversion from internal interface to 4 copper pairs are built in. You just need the transformers. PON, yeah, PON port. It's important because this is a PON device. And we have a different PON technologies. So very often modern chipsets have all PON possible by the chipset itself. GPIO controller, okay, you need to turn on a LED to show that the power is up or the port is up, so there must be a GPIO controller. Sometimes there is also a voice controller to do like the DSP operations for, or if you have a voice port. sometimes inside the SoC, there is already DDRAM, inside built in. So they put in a one enclosure RAM, not a flash, RAM and the SoC. Depends on the model that is used. And the PHY, that's a physical layer device. It is like, maybe you have seen sometimes SGMI, high SGMI, or UXGMI interfaces. You need, this is two pair, I mean TX and RX. And to change them, convert them to copper cable, you need so-called PHY. It can be built in a chipset. Usually 1G are built in, but 2.5G or 10G are external units. They generate a lot of heat because these are very strong DSPs, digital signaling processors, in fact, inside. So they do the modulation, demodulation, all the coding. So it is consuming a lot of power and generating a lot of heat. So with external PHY chipsets, if they are necessary, the device will generate more heat and consume more energy. Shortly, I mean, it converts 2-pair serial to 4-pair Ethernet, the PHY chip. Now, okay, it changes colors. Maybe this display is modifying the colors because I can see them a bit different here. I'm not sure about pictures, but later on. Okay, SoC structure, so it's a more or less structure. We have cores, so CPU cores can be 1 to 4 of them, sometimes with multi-threading, so you see more of them. GPIO controller, UART, so you can connect with a console port to the device, to the board, just to have like a terminal to the Linux, get to the Linux, for example. Flash controller, SPI, serial. Now modern chipsets, they support just a serial flash. Can be in a simpler solutions NOR, or in a more advanced solutions it's NAND, because NAND has a larger capacity. The quality of the memory inside, in fact, is worse because it considers that there could be like bad blocks by default, but they also have additional protection mechanisms to provide the error correction. And DDRAM controller. DDRAM can be external to the chipset or can be built in. Depends on the solution. There is some internal bus that all these units, they exchange messages, like when you talk to registers, so it sends information how the registers are to be configured. Switch core, NAT engine, if it is implemented, if the NAT engine is to be used. So if it's supposed to be able to be used as a router, it will have this NAT engine. I put here the all-PON PHY, because all-PON today is like GPON, GEPON, XGPON, XGSPON, 10G-EPON, symmetric and asymmetric. So we have a lot of technologies. Okay, there is also a new one for the new chipsets like 25GS, but it's not the case of most popular chipsets that we see on the market. So chipset can do any PON. Now, if the device is supposed to be GPON or XGSPON, the different lasers, optical modules will be used. But very often the same chipset can serve as a GPON or XGSPON, especially when there is SFP cage for optics. Not optics on board, but the optics which you can replace. So then some of the chipsets which have all PON can do all PON. And gigabit Ethernets, usually these are like 4 gigs. And sometimes you have extra interfaces to connect external PHYs to make like 2.5G or 10G ports, external, additional. And some I2C, MDIO to talk to these chipsets, to talk to the transceiver, to be able to read, write some kind of information that is necessary, like read optical signal level. This is an example of very simple ONT. SFU, layer 2 only, with a Realtek because we work with Realtek. 9601D. It has NOR flash, very little one. I mean, it has 16 megabytes. And PON transceiver, this is the part. Here is a laser module, and here is a driver. It's also important chip, driver for this laser. Here you read the optical signal level from this chipset. It's also in all the SFPs. You have such a chipset inside. And yeah, that's it, because this chip needs additional transformer. Here it is, this transformer is simplified, and you have one G port. Very simple construction. This chipset has built-in RAM, a little bit, just 32 megs. It's enough. And can be a router, but very limited, because maximum number of NAT flows is like 4K. And today, when you open a web browser, there is thousands of connections. So it's not enough. So I don't use it for layer 3. I just use it for layer 2. It's very good, one of the best on the market, does everything what is necessary. And we pass all the tests, even with Orange and the other operators. They have a very strict tests for... They provide equipment when they do the tests, and we are passing, our competitors are not passing. That's very good chipset. Similar one, sorry. Okay. I wanted to mention that, in fact, this chipset has two ports. One is with internal PHY, but the other one needs external PHY, where you can connect 2.5G interface. So the same chipset on the same board was reused to design device that is very similar, but has additional PHY chipset to support 2.5G. We don't use the 1G port. It's not connected. It's just this way. But it has additional chipset, which is the external PHY, which generates more heat. That's why users may say, okay, this one is hotter than the other one. Yeah, because it generates more heat. The other flash is not used in a production model, but it's not necessary. Similar chipset, very similar, it's almost the same. A 9601C. It doesn't have the copper port. It just has the high SGMI for the SFP connector. And that's it. It's the same structure. And it's slower, not 300 megahertz, but 112, because we want less energy, less heat to be generated by such SFP. It's very, very simple. But the same SDK, the same software, the same code can be running on both, but some tuning is necessary because of some elements are missing here, and the other communication is used. This is the example of the use of another chipset, which also has a RAM inside, but this one can do more routing, can do 32,000 of NAT flows if necessary, can do TR69, the other things, and uses different software development kit. That was a test board. They changed the chipset from 28 nanometers to 22 nanometers, but there were some also additional registry changes inside, so we had to adjust the software for that. What we have, simple. Chipset, transformers here, and 4 ports. Additionally, this is a SLEEK, so the chip for voice, and 2 voice ports. Laser, chipset for the laser, and that's EEPROM for this chipset, and that's it. This board used to be also with Wi-Fi, but we said, okay, we don't need the Wi-Fi because it was Wi-Fi 5. We said, oh, no, we just need without Wi-Fi, and that we could reuse the same project. It was cheaper to do it. Now, here is example of XGSPON, single port. Chipset is Realtek 961C, and interesting thing, this chipset is built with Cortina. Realtek owns Cortina. Cortina, American company who does chipsets for PON, was bought by Realtek, and now the new Realtek chipsets, they take some part of intellectual property from Cortina, and they just add their own, and they build the chipsets which are branded as Realtek, but it's Cortina inside, a bit of Cortina inside. And here we have now ARM processors, ARM cores, 2 ARM cores. This chipset doesn't have PCI Express, so cannot be Wi-Fi, but can be also a router, and can be used for layer 2, for VLANs to be transported. That's very simple one. We have external PHY for 10G here, the main chipset, external memory. Here is a flash. This is NAND flash, transformer, and a 10G port. Optics is hidden here under this metal shield. Very simple construction, but not that simple in programming. A lot of tiny little issues, as usually. When the SDK is delivered, all the software code, source code is delivered. There are bugs, there are some things they didn't test. So we often have to do some reverse engineering, check, search. Sometimes we ask the support if we don't know how to change something, but we know what to change, but we don't know how to change it. It is a very time-consuming process to make it working properly, but we have a good, smooth, stable software for that purpose. And this one is exactly the same chipset, because this chipset also has built-in 4 ports, gig ports, and this one has these ports connected. So we have transformers and 4 1G ports. All the rest, I mean the PHY, chipset, RAM, flash, optics, it is the same. Now, shortly about optics. If we use the optics, which is for 10G, symmetric optics, it cannot do GPON or EPON, because they use different wavelengths. But with XGSPON symmetric optics and a symmetric optic chipset, which is inside the small one, the driver for the laser, you can make it like XG, 10G EPON symmetric, and 10G EPON asymmetric. They can work in 4 modes. So one of our devices, you can switch from any mode to any mode that is necessary to be used. But proper optics must be used. If the optics has a limitation, like maximum uplink speed is 2.5G, you can't make it 10G, XGSPON. Symmetric, you can't make it symmetric. Router. Okay, finally we have boards. We have received 6 boards for software development. So we decided to make also the Wi-Fi 7 router. Wi-Fi 6 didn't make sense today. We decided, okay, let's go to Wi-Fi 7. That's a quite new chipset from Realtek, 9607F. The difference from the previous one is that it has ARM cores, and it's like Cortina inside, two cores. And it has built-in RAM inside. Wi-Fi chipsets are here on the right side. This is for 5 gigahertz, and it's a big one. I will tell you later why. And the smaller one is for 2.4 gigahertz. You can see 4 1 gig ports, and 2 red ports are 2.5G. But that's the development port. We have optics, and we have 2 ports which are 2.5G. But the production will be either optics or 2.5G WAN. So in the case we have 2.5G ports, we will not use optics. If we use optics, there will be just one 2.5G port on the board. But in fact, both of them can work in the same time. All of them can work in the same time. And here are the 2 converters, the PHY chipsets which I mentioned at the beginning, that convert high SGMI to copper twisted pairs that you connect your devices. And it will be able, so it will be able to work as Wi-Fi mesh controller, and in the future, because they have to update the SDK, the Realtek has to update the SDK, also as agent. So multiple options with the same hardware could be with just a different software to be done. That's a block from, that's the example of, okay, if the Wi-Fi router ONT with, it will be ONT, so optical, there will be no 2.5G WAN, only 2.5G LAN, and optics. Here is the chipset. Here you can see the BOSA, so optics and the controller for the optics. Flash, some LEDs, button, additional 4 1G ports, FXS port for telephony, USB, and Wi-Fi. Wi-Fi is interesting. I will tell you why. Sorry, that's a Wi-Fi 7. Wi-Fi 6, both chipsets for 2.5G, 2.4 gigahertz and 5 gigahertz were connected directly via PCI Express to the main SoC. Here, we have just one connection. Why? Oh, sorry. Okay, just we will come back to that. And if Wi-Fi router will be with 2.5G LAN and 2.5G WAN, it will not have optics. So this part will not be added. That's just the difference between these two final solutions. Look, there is a PCI Express generation 2 multiplied by 2. So in total, it can do 12 gigabits per second. But this PCI Express is connected only to the part which is responsible for 5G. And 5G controls 2.4. Why? Because in Wi-Fi 7, it is much more complicated. And now you can have both bands working in the same team. So in the same time, a receiver and transmitter can use 2.4 gigahertz and 5 gigahertz for transmission. So they can combine it and aggregate bandwidth. So that's why it is done in this way. One of the chipsets, so the big one, for 5 gigahertz, is a controller for entire Wi-Fi. And it is connected to a main SoC with 12 gigabits throughput to do it. And now, this chipset has own, I say probably because this is what I don't know exactly, ARM-M cores. So there are like separate cores running in the chipset for Wi-Fi, and it runs own operating system for the Wi-Fi subsystem. Take a look. You can see it's RTOS boot. So when it boots up, the device itself, all the entire router, it also reports that the chipset, which is inside, also has booted up with real-time operating system. So additional dedicated operating system just for the Wi-Fi subsystem. Okay, software, shortly. Well, there are two SDKs which we use, like Luna SDK for older Realtek solutions, mostly for the GPON, so SFU for layer 2, and the unified SDK for all new Realtek chipsets and some older also supported. But take a look. Older SDK should be my English, almost 700 megs of source code, and the new one, 2.5 gigabytes of source code, and it's compressed. It's all compressed in TargZip, so it's much larger when you decompress it. And it doesn't include like OMCI or EPON or Wi-Fi drivers. It's additionally some kind of 200 megs extra of a code. And it's Linux-based, both. Everything here is at the moment Linux-based, the most popular system, but it takes a time until it boots. I mean, it's usually like 1 minute or could be to boot all the systems and the subsystems. It's a long time. And something interesting, 25 GSPON. The only vendor today who sells that the kind of OLT is Nokia. But there is 25 GSPON, so symmetric 25G. We have it in a lab, and it works. And that's an example of such a chipset. Main SoC is now Cortina, pure Cortina. Interesting, no more Linux. They put real-time operating system. But why they switched to RTOS? Because a requirement from some of the telecoms was that entire router, if you make a router, this is just layer 2, entire router must boot up within 15 seconds. 15. That's it. 15 seconds and everything must be ready. You can't do it with Linux. But with real-time operating system, yes. And the different cores are used. Now this is ARM-M inside. And they can be very power efficient. They can slow down to 100 megahertz or can run also as 800 megahertz cores inside. And this device has one port which is 10G, multi-rate for the copper connection, or SFP 28 cage connection. Cage. So there is you can choose either or. So if you put in the SFP, you can't use 10G copper port. If you remove the SFP, you can use 10G SFP port. In our tests, internal tests, we could see 19.9 gigabits per second with the iPerf. But it was rather like a iPerf limitation. This could be used for business. Okay, the next step, in fact, will be 50 GPON, which is asymmetric, 50 to 25. But there are no chipsets yet for ONTs. Only some FPGA projects. For OLTs, yes, but for ONTs, no, not yet. Okay. We have a blog. You can scan also the code to see there. It's in English. We write some interesting information of some OMCI logs, what's happening, how it looks from commands and from log and the MIPS configuration perspective, what's happening in the device. Just recommending to read this information. And we support also ISPs if we can. I mean, we don't know everything. There is no way to know everything. But if ISPs, like from Ukraine, you have some problem, and we may know how to help, it is not a problem to write to us. And if we know the answer, we will say. If we don't know, we will say we don't know. Sometimes we can't help, but we do it. I mean, we also learn from this channel. And yeah, support at LeoLabs.pl is the mail. That's my lab. Just do it. Yeah. And okay, also shortly, interoperability process. Unlocked OLT is just the first step. If the OLT it can accept other ONT. There's a lot of different things like services may work, but only partially. DHCP, for example, DHCP request with broadcast flag. When you send the DHCP request, some devices set so-called broadcast flag, which says to the server to respond not with unicast, but with broadcast. And you may be surprised how the devices can handle that or not, the response. Or optical signal level with Huawei OLT. It's not standard. They don't follow the standard. They just choose their own standard. If you change the vendor ID, for example, so if you pretend to be Huawei, for GPON, it works for GPON, then to read optical signal level, you need to have some reversed solution. Or reading MAC addresses table from OLT, I mean from OLT and ONT port. Also, it's an extension to a standard solution. But they say everyone is standard. No. The standard is interpreted in private ways. Something that I have to say about me. Do you know the ERLAC, Roam Like at Home? Ukraine will be in ERLAC from January 2026. And it was me, first article. Here's the link. It's in Polish, but you have to translate it. It was in April when the war started. I wrote, why not to join the Ukraine to Erlach? That's a whole article. And then it was sent to the officials in Poland. Then they forwarded that to Brussels. And finally, at the end of 2025, it's done. So if you travel to Poland, to any EU country, also Moldova is included in that, you will just be like at home. So yeah, that is something that I was fighting for, and it's done. And thanks for my wife. My wife designed the logo for both company and the device. Thank you.
So, thank you very much to Marcin Kuczera. Ще раз. Дякую вашому оплеску. Це вже друга наша презентація, другий рік. І дуже йому дякуємо.
Дякую.